now recording. Okay, so this is theorem 4.2, Poisson's limit law. So P varies with n, so that n times P is lambda, where lambda is a positive constant. Then the limit of the binomial probability function, x and P, is equal to the value of the Poisson probability function P of x comma lambda. Okay. Okay. So not only does the Poisson probability function approximate the binomial when the limit of the binomial is equal to the Poisson. Okay, so that means that if n is very, very large, then these values have to be very close to these values. Okay? Because as n is going to infinity, b is going to p. And so if you take little n large enough, then these b's will be very close to p. Okay. Okay, so this is 4.5.5.2, which is on random phenomena with Poisson distributions. Okay, so these are examples of random phenomena with Poisson distributions. Okay, some of them are a little weird. Okay, so the first example I'm going to mention is the number of incoming phone calls within a fixed time interval at certain switchboards. Okay, so the number of incoming phone calls within a fixed time interval at certain switchboards. Okay. Another example, which is example 5 in the book, so I'm going to write 5. The number of fish caught in a day in certain regions. Okay. And example 11 is the number of emergency patients on a given day in a certain hospital. Okay, so some random variables are essentially binomial random variables with large parameters n and small parameters p. Hence, they are given essential, since they are essentially Poisson random variables. Okay. Okay. Comma here. So example 4.16, let x be the number of misprints on a page selected at random from a large book. Explain why it may be reasonable to assume capital X is a Poisson random variable. Okay, so suppose each page has n letters, page of the book has n letters, numbers, and other printed symbols. Okay. So if an error in printing a symbol is a success in a Bernoulli trial of probability probability P less than 0.1, and little n is greater than 100, so there's more than 100 letters on the page, and X, which is the number of successes in n Bernoulli trials, So that's what X is. Then the probability of X equaling some fixed little x is equal to the binomial probability function xn comma p. Okay, so what this is saying is that you have a book where you assume each page has n letters, numbers, and other printed symbols. Okay, so the error, when you have an error, it's considered a success, and you assume the probability of success, the probability of an error, is less than 1/10, which is reasonable, and that the number of printed symbols on each page is greater than 100, which is also reasonable. And you let X equal the number of successes in n Bernoulli trials. Okay, the number of errors essentially. So So it's the number of errors on the page. Okay, so each printed symbol is itself a trial. So if you had a page with 200 letters in it, then that would mean that you had 200 trials, and that by the end of the page, after 200 trials, the number of successes, the number of errors on the page. Okay, so the probability of little x many successes is just the value of this binomial probability function, right? You want X number of errors on the page with n printed symbols where the probability of an error is little p, okay? But these meet all three conditions from earlier, okay? So all three conditions of the binomial probability function being approximately equal to the Poisson probability function are satisfied in the problem. Okay, so the three conditions are, first we want little n to be large. So n is large, little p is small, and lambda, which is n times p, is equal to, I should say, is approximately right, we're saying the probability is less than 0.1 and n is greater than 100. So you can kind of think it's kind of around 100 times 0.1, which is 10. Okay, so lambda is moderate, right? We're making p very small and n relatively large, so that its product is still moderate, right? But n is large, p is small, and lambda is moderate. And in that situation, you have that these two are approximately equal. Okay, so thus, it is reasonable to assume that the probability of capital X equaling some fixed value little x is equal to this, but also that it is approximately equal to the value of the Poisson distribution. Okay. And so this is the conclusion. This is the thing that okay, so the thing that we are assuming is that approximation. So the probability is approximately the Poisson distribution. Okay, for short, we say here that the probability is just, you might see that when somebody approximates something, they use the equal sign. When you're writing equals, it's meaning approximately equal. We're assuming that the probability is this because it's really approximately that. Okay, so we can assume that X is a Poisson random variable. Okay, so we want to show why it's reasonable to assume X is a Poisson random variable. That's because it can be approximated very well by a Poisson distribution function. Okay. Okay. So that's any questions about that? Okay. So the next thing is on Poisson processes. Okay. So if a physical process satisfies 3 conditions, then the random variable capital X that represents the total number of occurrences that represents the total number of occurrences of this phenomenon. Within the fixed period of time or fixed region of space is a Poisson random variable. Okay, so these are the 3 conditions. One, the number of occurrences of the phenomenon in any 2 or more disjoint intervals of time or regions of space must be independent of each other. Okay, so the number of occurrences does not depend on each other. So regardless of what happens in one region of space or in one interval of time, it has no bearing on what happens in the other region of space or other interval of time. That's the first condition. 2, second condition. The probability of at least one occurrence of the phenomenon during any subinterval of length 1 over n is always the same. Also, if P sub n is equal to probability of at least one occurrence of the phenomenon during any 1 over n length interval, then there is a constant lambda positive such that the limit as n approaches infinity of n times p sub n is equal to lambda. So the probability of at least one occurrence of a phenomenon during any subinterval of length 1 over n is always the same. Also, if p sub n equals the probability of at least one occurrence of this phenomenon during any 1 over n length interval, then there is a constant lambda positive such that the limit as n approaches infinity of n times p sub n is equal to lambda. So the limit of the product of n times the probability of at least the one occurrence of the phenomenon during any 1 over n length interval is equal to lambda. That's the second condition. The third condition is that the probability of 2 or more occurrences in any given very short interval of time must be smaller than the probability of just one occurrence, plus in any given sufficiently small length interval of time, the probability of two or more occurrences must be about the same as the probability of one occurrence. So here's the third condition. The probability of two or more occurrences in any given very short interval of time must be smaller than the probability of just one occurrence. Okay, so no matter how short of an interval you choose, the probability of two or more occurrences is less, has to be strictly less, not equal, strictly less than the probability of just one occurrence, right? So requiring that more than just one occurrence happens means that its probability cannot be greater, right? You're assuming the first occurrence and another one. Okay, so the probability can only go down. It could be the same or it could be less, but here it's saying it has to be strictly less. Plus, in any given sufficiently small length interval of time, the probability of two or more occurrences must be about the same as the probability of one occurrence. So not only is the probability of two or more occurrences strictly less than the probability of one in arbitrarily small length intervals of time, it's less, but it's close. So it's smaller, but very close. That's this assumption, and that's the third assumption, okay? So we have these three conditions, okay? And so the conclusion, well, so if the three conditions are satisfied, then there is a constant, lambda, which is positive, such that for each given value of t, the distribution of x sub t is the Poisson distribution with parameter lambda t. That is, the probability of your random variable x sub t equaling to little x is equal to the Poisson probability function with parameter lambda t. So that means it's lambda t raised to the x times e raised to the negative lambda t divided by x factorial. Okay, so the conclusion is that, okay, so if the three conditions are satisfied, okay, so if the three conditions are satisfied, then there is then all this happens. Then there is a constant lambda positive, such that for each given value of t, the distribution of x of t is the Poisson distribution with parameter lambda t. That is the probability that your random variable x of t equals little x is equal to this. This is the Poisson probability distribution with parameter lambda t. Okay, so reminder, the Poisson probability function looks like this. It says that the probability of a random variable, I'm going to call it y, that way it looks different than the x I just used above. It's just another letter. There's no difference. The Poisson probability function with parameter lambda looks like this. So the probability that your Poisson random variable is equal to this number, little y, where it has parameter lambda, would be lambda to the y, e to the negative lambda divided by y factorial. Okay, the parameter is the lambda, and the value of your random variable is this little y here. So here our random variable is x of t instead of y, but we're considering its probability equals little x. So instead of y, there's x. So the exponent here is x, and there's x factorial. But the parameter is lambda t instead of lambda. So instead of the base here being lambda, the base is lambda t. Instead of the exponent being negative lambda, it's negative lambda t. Okay, so from the original Poisson probability function, we have that these, for each t, we have an x of t, which is a Poisson random variable with parameter lambda t, meaning its probability function has that form. Okay, so this is for x equals to 0, 1, 2, 3, and so forth. Okay, just like in the original one, this is for y equals 0, 1, 2, 3, and so forth. Okay, you can plug those values in. Okay, so let's do an example. So this is example 4.19. The number of telephone calls arriving within a time interval of length t in minutes is a Poisson process x of t with lambda equal to. So part A is find the probability that x of 5 is equal to 0, which is the probability of 0 telephone calls in 5 minutes during any 5-minute period. Okay, so the 5 here is telling you the amount of time that you're considering. So the 5 here is, since it's length t in minutes, since the unit of time is in minutes, the 5 represents amount of minutes. Okay, so that's told to you in the problem, or when you're doing something, you would tell the person reading what your unit of measurement you're using. So our unit of measurement for time is minutes, and so 5 here denotes the number of minutes. So in 5 minutes, we're considering intervals of 5 minutes, and we want to know the probability where in any 5-minute period, the number of telephone calls is 0. Okay, so before I gave examples of Poisson processes. And so one of them was the number of telephone calls arriving within a time interval of length t. Okay, so this situation I mentioned earlier here. Okay, the number of incoming phone calls within a fixed time interval at certain switchboards. So this is an example of a Poisson distribution. So using that example from earlier, we have a Poisson distribution. And so this probability, we can calculate using the Poisson probability function. So what we want is the probability that x sub 5 is equal to 0. And so that's equal to, and so what that's equal to is, so okay, and so this is going to be lambda times t raised to the x power times e raised to the negative lambda t over x factorial. Okay, so over here, Okay, so if the three conditions are satisfied, then there is a constant lambda positive such that for each given value t, we have this distribution. We have a Poisson distribution with parameter lambda t. Okay, so there is a value of lambda in which the probability distribution takes this form. Okay. Okay, so we have lambda equals 2. So we plug in lambda equals 2. And so we get 2t raised to the x power, e raised to the negative 2t divided by x factorial. Okay, and so here, the number itself is 0. So you plug in a 0 here for x. Okay, and 5 is the value of t. So this will be 5. I'm going to put a symbol here, 5. And this is 5 there. Okay, so t, so above, t is equal to 5, lambda is equal to 2, right? We're given lambda equals 2 right here, but we know that t is 5 from there. So you just plug in lambda and t, and x equals 0. And so now you calculate this probability. And so 0 factorial by definition is 1. 2 times 5 is 10. You have 10 raised to the 0 power times e raised to the negative 10th power. So 10 to the 0 is 1. And so you get this is equal to e to the negative 10th power. Okay, and so that's e to the negative 10th power, which is equal to 0.000045. That's an approximation. It's rounded to the nearest 6th decimal place. Okay, so that's part A. Any questions about that? Okay, so B is find the probability that x sub 1/2 is greater than 1. Okay, you sure? Okay, so so this is equal to the probability that more than one call in any 1/2 minute period. Okay. Right. So the 1/2 is the interval of time, and the 1 is saying for the number of calls, and greater is saying that it's going to be more than one call in any 1/2 minute period. So we want the probability of that. Well, the probability that x sub 1/2 is greater than 1. The probability of getting more than one call in any 1/2 minute period is 1 minus the probability of getting at most one phone call in that 1/2 minute period, any 1/2 minute period, right? So that's equal to 1 minus, well, there's two possibilities. You could either get in any 1/2 minute period, you could either get 0 phone calls, or you could get 1, right? So the only that if it's x less than or equal to 1, then if x sub 1/2 is at most 1, it could either be 0 or it could be 1. Okay, so this probability at most 1 is the sum of the probabilities of it being 0 and 1. So it's 1 minus that sum. So the minus sign distributes. Okay, so just adding another step just to make sure that there's no confusion here. Since it's the sum there, it's 1 minus the first and also minus the second. We're subtracting the sum, which means we subtract both of them from 1. Okay, so it's just a matter of finding each probability and plugging them in and getting 1 minus the first probability minus the second probability. And that's the answer. Okay. And so for this, we again use the Poisson probability function, and we plug in the values for each. Okay, so t is 1/2 for all of them. So there's going to be a 1/2 here. There's also going to be a 1/2 here, right? So t is 1/2. Lambda is always 2. It's given in the problem. So lambda is 2. Okay. So for both of them, the value of t, which is 1/2, and lambda is 2 is the same. But for the first term, this term, x is 0. So for this term, x is 0. So I'm going to color this in red. And so that's going to correspond with this x here, which is going to be in red. Okay, and now this x is also going to be 0, okay, because of that right there. So lambda, is I guess I'll put this as blue. And so since lambda is blue, lambda is always 2. So that would go here. This is the lambda in the formula, because lambda is 2. We got this from the beginning. Okay, the 1/2 is the value of t. It's hard to see that, though. It's hard to see that 1/2. So I'm going to change the color to purple. You can see that better. Okay, so that's a 1/2. So there's a 1/2 here, 1/2 here. They're all 1/2s. Okay. So color this in purple. And so then that corresponds with this 1/2 here, this 1/2 here. Okay, and then so here we already have the 1/2 here. That's from the value of t. Okay, so that's purple. 2 is lambda, so that's still blue. This is blue. Okay, but now the value of x is now changed to 1. And so now x is now going to be 1. And so that's the difference. Okay. So the difference is the value of x. So while here it was 0 in red, now it's 1. Okay, and so now you just compute this. So this is 1 minus 2 times 1/2 is 1. 1 to the 0 power is 1. 0 factorial is 1. This is e to the -1. Okay, and then minus the other term. 2 times 1/2 is 1. 1 to the first is 1. 1 times anything is this. So the numerator is that. The denominator is 1 factorial, which is 1. So the whole thing boils down to that value. And 2 times 1/2 is 1. So this is also e to the -1. This is minus e raised to the -1. So now you have 1 minus e to the -1 minus e to the -1. And so if you compute that, that's also 1 minus 2e to the -1. And that's equal to, that's approximately equal to 0.26424. Okay, and so that's the answer to B. Okay, so this is an example of when you recognize a situation as being a Poisson process, and then given the parameter, you calculate probabilities using the Poisson probability function. So the next one is 4.5.5.4, which is the parameter lambda. Okay, so if the numerical value of an experiment is a Poisson random variable x, and if the experiment is repeated a number of times, we expect the average value of capital X to be lambda. Okay, so you expect the average is tending to lambda. If you do repeat the same experiment enough times, eventually the average value will be very close to lambda, and so you can assume it is lambda. Okay. Okay, so that new topic. Good. So 4.6 is on the cumulative distribution. Cumulative distribution functions of discrete random variables. Okay, so this is easier than the last section. Okay, so cumulative is 4.6 on cumulative distribution functions of discrete random variables. So first the definition. So this is definition 4.8. It says the function capital F of x is equal to the probability that your variable capital X is less or equal to little x. This is for negative infinity, less than x, less than infinity. And so this is called cumulative distribution function. So this function, capital F of x, is called the cumulative distribution function. Not just because it has a capital letter, because how we defined it. It's equal to the probability capital X is less or equal to little x. Sorry, for any finite x. For any x between negative and infinity means for any finite value of x. Okay, so example 4.20. Finding the cumulative distribution function. So here we let x be a discrete random variable, right? The sample space is a discrete sample space, meaning it's finite or countably infinite. So let x be a discrete random variable whose only positive values are -1, 2, and 5. Suppose the probability function of capital X is the following. So your probability function is little f of x, and it's defined by a piecewise function. Which is the following. So it's equal to 1/4 for when x is equal to -1, 1/2 for x equals to 2, and 1/4 for x equals to 5. Okay. So saying whose only positive values are those three, meaning it's the only place with any non-zero probability. Okay, for any other values of x, the probability is 0. Okay, so these are the only three values of x in which the probability is non-zero. Okay, so the question is the problem is find the cumulative distribution function of capital X. Okay. Okay, so we want to find the cumulative distribution function. That's this guy. Capital F of x equals the probability that capital X is at most little x. So to do that, let's look at particular cases. Okay, let's look at case one. Case one, if x is strictly less than -1. Okay, so if little x is strictly less than -1, then the probability that capital X is at most this number little x, which is strictly less than -1, is equal to 0. The reason why it's equal to 0 is because the smallest value of little x in which there's some positive probability is x equals -1. The probability that capital X equals -1 is 1/4. But for any value of little x less than -1, the probability is 0. And so the probability that capital X is at most a number which is strictly less than -1 is 0. Okay. Case two. If -1 is less or equal to x less than 2. So if x is greater or equal to -1 and less than 2, then x falls somewhere between this -1 and this 2. Okay, it cannot be 2. It could be -1. Okay, so the first positive probability is that x equals -1, and it's 1/4. Now, for any other value of x strictly between -1 and 2, the probability is 0. And so the probability that capital X is at most little x is equal to the probability that capital X here is equal to -1. Because x is greater or equal to -1, so it contains this x value, but it does not contain 2 and it does not contain 5. It's strictly less than 2. And so when you compute this probability, the only x value that matters is when x is -1. So the only one of those three values, which is in this interval, is x equals -1. And so it's equal to that probability, which equals 1/4. Okay. Now, case three, it says if 2 is less or equal to x, strictly less than 5. So if x is at least 2, but strictly less than 5, and we want to find the cumulative distribution function for those values of x at least 2, but strictly less than 5, well, what that's going to equal is the probability that x equals -1 plus the probability that x equals 2, right? It's probably x at most this x value. And so if it's at most something at least 2 but less than 5, that means you add the probabilities when it's -1 and when it's 2, but not when x is 5 because it's strictly less than 5. Okay, so x is at most little x, but little x is less than 5, and so you do not add the probability x equals 5. So this is sum of those two probabilities, and so that's equal to 1/4 plus 1/2, which is equal to 3/4. So capital F of x for x values here is equal to 3/4. And then case four, is that if x is greater than or equal to 5, then the probability that capital X is the most little x, well, that's equal to, well, if x is greater than or equal to 5, then since capital X is at most this value that's greater than or equal to 5, you're going to add all three probabilities. You're going to add these two, but you're also going to add the probability that x equals 5, because little x is greater than or equal to 5. Yep, so right, so it's 1/4 for the probability of x equals -1, plus 1/2 the probability of x equals 2, plus 1/4 the probability of x equals 5. So you add them up and you get 1. Okay, which is what we should get. Okay, and so for these four cases, for these four subintervals, we exhaust the entire real line, meaning we separated it into 4 subintervals that were disjoint, in which their union is the entire real line. Okay, so every point every value of little x is covered in one of these four cases, and it's only in one case. Okay, so these cases are disjoint in a sense. Okay, so the conclusion is that for negative infinity, less than x, less than infinity, we obtain the cumulative distribution function. Okay, and so there will be four lines here. So for case one, the value of f capital F is 0. And that's for x less than or equal to -1, as we established in case one, right? So in case one, we found this. Okay, and so that's this line right here. Okay, in case two, we determined this. And so in the second line, we say that capital F of x is equal to 1/4 if -1 is less or equal to x, strictly less than 2. In case three, which I'm going to color in green, okay, the colors may look green. Okay, so then 3/4, the I, so at least my eye did. Okay, so then green, so it's 3/4 for for 2 less or equal to x, strictly less than 5. And then lastly, in black, it's 1 for x greater or equal to 5. Okay? Be consistent with words. I'm going to replace if with for. For and if mean the same thing. Okay? Sometimes people put for at the top and then maybe put a comma, but then not write for, keep writing for. I kept writing for just so it was clear the argument I was making with each number. Okay, so it makes sense. Just gonna space this out. Okay, so that way it's clear. Okay, and so from these four cases, we're getting these four subintervals there. And so we've now found capital F of x as a piecewise function. So that is an example of a cumulative distribution function. Okay, so hopefully you're taking some notes. So hopefully you wrote down this function. So what I want to do now is graph this function. Okay, so I can't copy, I don't think I can copy and paste that into whiteboard. So what I want you to do is have this written down. So I'm going to graph this on the whiteboard. Okay, capital of x is going to be 0 for x less or equal to -1, 1/4 here, 3/4 here, and 1 there. And so let's see visually how a cumulative distribution function looks. Okay. Okay, so I'm going to just label some things in here. So that's going to be -1. This is going to be -2. This is going to be -3. You don't have to have this is 0. So I'm making that here. And now I'm going to make that 0, this 1, this 2, this 3, this 4, this 6, and so forth. Okay, the probabilities I'm going to put here. So I'm split up into fourths. This is going to be 1. That's 1/2 in the middle. This is 1/4. This is 3/4. These are some of the values that we saw before. So you start with 0, right? So here we had 0 for x less or equal to 1. Capital F of x is 0 for x less or equal to -1. So it's for x less than or equal to -1, capital F of x is 0. So I'm only using different colors. It's all this one graph. I'm using different colors. So you see the correspondence between the part of the graph and the piecewise function I wrote down on Word. So the colors are corresponding to Word. So that's the part for x less or equal to -1. For x at least -1 and less than 2, the value is 1/4. Okay. Oh. This is strictly less than here. So this is a less than symbol here. Okay, so that's a less than symbol. Okay. Everything else is good. Okay, so this is a less than symbol. This is here. Okay. That's because the probability at x equals -1 is 1/4. So before x equals -1, when x is less than -1, it's 0. But then it changes at x equals -1. Okay, so it's a less than symbol. So I'm going to fix that. So when you have put like an open ball. So I'm going to redraw it. Okay, so so at -1, we put an open ball signifying that it does not include that point. And we draw a line going left. Okay, so that's a line. Okay. So then when it's 1/4 for x greater than or equal to -1 and less than 2, 1/4. Okay. It's going to be blue. Okay, so the next part is blue. The value is 1/4. We're including this value up to 2, but we're not including at x equals 2. So we have that there. Okay. So next is in green. It's going to be from at least 2, but strictly less than 5, 3/4. So from 2, including 2, not including 5, value stays constant, 3/4. Okay. And then for x greater than or equal to 5, including 5, value is 1. That's in black. So it's going to be in black, and the height is going to be 1, and it's going to include x equals 5. And it's all x is greater than or equal to 5. So you get it right. And the arrow keeps going in that direction. Okay, so this is a graph of the cumulative distribution function. So this is a graph of the function y equals f of x. I'm using pink just so I don't want to use black because I use black for that arrow. So this is capital F. So this is the graph of y equals capital F of x. Okay, and so it's a non-decreasing function, meaning that as you go to the right, either the value stays the same or it increases, right? So this is a non-decreasing function. Okay, it's a right continuous function. So the limit on the right exists, but the limit on the left may not exist. Okay, so if you're approaching a point from the right, the point you're heading towards is part of the graph, right? The right-handed limit exists, but the left-handed limit doesn't have to exist. As you approach x equals -1 on the left, the value you approach is not the same as the value at x equals -1, right? So right-handed limits exist, left-handed limits may or may not exist. They do not exist everywhere. So we only have right-handed limits. That's calculus for this function. Okay, so that's how cumulative distribution functions behave. Okay, so this is a graph of one example of a CDF from this example. Okay, so this is an alternate definition of the cumulative distribution function of a discrete random variable. So let little f be the probability function of the discrete random variable capital X. The function capital F of X, which is equal to the sum over all t less or equal to x of f of t for negative infinity strictly less than x, strictly less than infinity, just meaning any finite x, or for any finite little x. That function capital F, defined in that way, is the cumulative distribution function. Okay, the sum is over all values of t less or equal to x, for which f of t is defined. So there are points in the course where we use calculus, right? So sometimes you are required to know calculus for this course, yes. Okay, so so this sum here, it's summing over all values of t that are at most little x, such that f of t is defined. Okay, so in the next example, we're going to compute this and see what it means for the sum of all values of t at most little x, such that f of t is defined. Okay, so this is example 4.21, finding the probability, probability with a cumulative distribution function. Okay, so well, we will use that. I'll explain that more soon. Okay, so just want to do this example. Actually, okay, fine. I'm going to do a side example explaining the last definition. Okay, so this sum, right? So, okay, so let's say you roll a spare six-sided die. Okay, and you let capital X equal to the value that appears on the die, right? So we already know that the probability function for this example is 1/6 for every x. So x equals 1, 2, 3, 4, 5, and 6. Right? When you roll the die, the probability of any of those 6 numbers is 1/6. So PDF, little f of x is 1/6. So let's say you wanted to calculate capital F of x, right? Well, let's say you want to calculate capital F of 2. Okay, so capital F of 2 is the probability that that capital X is at most 2. Okay, well, then by this definition, it's equal to this sum. But it's the sum over all t less or equal to x, but here x is 2 of f of t. So the sum, the summation above is done over all values of t such that t is less or equal to 2 and f of t is defined. Okay, so f of t is only defined on values 1, 2, 3, 4, 5, and 6. And so we're not going to evaluate f of 1.5, right? The only values of t at most 2 that are defined here are 1 and 2. And so that means that this is the sum of all f of t, such that t is at most 2, and t is something from this list for this problem. So that means it's only t equals 1 and t equals 2. So this is equal to f of 1 plus f of 2. And so since each of them is 1/6, it's 1/6 plus 1/6, which is 2/6, which is 1/3. Okay? So then this is a side example of explaining the summation notation. You're just adding all the probabilities for each t at most 2, because you're finding capital F of 2. If this is capital F of 3, this would be replaced with a 3, and you do f of 1 plus f of 2 plus f of 3. Because f is only defined on values 1, 2, 3, 4, 5, and 6 in this experiment. Okay, so here in example 4.21, you want to find probabilities with a cumulative distribution function. So let capital X be a discrete random variable whose cumulative distribution function is the following. So you're given that the function, your CDF, cumulative distribution function, is equal to, so we point out here that an abbreviation for cumulative distribution function is CDF. Okay, so cumulative, C for cumulative, D for distribution, F for function, CDF, cumulative distribution function. Okay, so let's say your CDF is defined this way. Capital F of X is 0 for X less than -3. It's 1/6 for -3 less than or equal to X strictly less than 6. 1/2 for 6 less than or equal to X strictly less than 10. And 1 for 10 for X greater than or equal to 10. Okay, so in part A, you want to find the probability that capital X is less or equal to 4, the probability that -5 is strictly less than X less than or equal to 4, the probability X is equal to -3, the probability that X is equal to 4. Those 4 probabilities. So the probability that capital X is at most 4 is equal to, well, that's capital F of 4. That's the meaning of capital F of 4. Capital F of 4 is probably X is at most 4. So according to this piecewise function, capital F of X, when X is 4, 4 falls in this interval. Right? 4 is greater than or equal to -3 and less than 6. And so it's saying that capital F of X there is 1/6. So this equals 1/6. Okay. The probability that -5 is strictly less than X and less than or equal to 4 is equal to the probability that X is at most 4 minus the probability that X is at most -5. Okay, so why is that? So on whiteboard, I'm going to explain this. I want to show the probability of this interval is probability X is less or equal to 4 minus the probability X is less or equal to 5. Okay, so if you're looking at an interval from -5 to 4, You want to know the probability of it being in this interval. Well, if you think about the probability of it being at most 4, right? If you have the probability that x is at most 4, it's the probability of that blue set, right? But if you subtract from it the probability that x is at most 5, if you subtract the probability that it's in this red region, x at most -5, well, then you're taking the odds of it being in the blue interval and subtracting the odds of it being in the red interval. And so that means that what's left is the probability that it's in blue but not in red. So that I'll put this in green. So this green region is the part that's blue but not red. And so that means that this is equal to the probability of the green region. Probability in the blue region minus probability of the red region is equal to the probability of the green region. And the probability of the green region is the probability that -5 is strictly less than x, less than or equal to 4. Yeah, you take the blue region, remove from it the red region, and you're left with the green region. Okay, so we have this equality here. Okay, and so that means you have this is equal to this minus that. Okay, well, each of these two probabilities is of the form P of x less than or equal to a number. And those are values of capital F, right? So both of those probabilities are values of capital F. This is probably x is at most 4, which means that's capital F of 4. This is probably x is at most -5, which is capital F of -5. And so it's equal to the difference of those two values. And so capital F of 4, because 4 is in this interval, it's 1/6, just like here. So F of 4 is 1/6, and then you subtract F of -5. Well, -5 is less than -3, which means capital F of -5 is 0. So it's -0, which equals 1/6. And so the probability that x is in this region, in this half open or half closed interval, because it's not including the left endpoint, but including the right endpoint, probability of it being there is equal to 1/6. Okay. The probability that x is equal to -3 is equal to, well, when the cumulative distribution function for any little x less than -3 is 0. So up to any number less than -3, the cumulative probability, the sums of the probabilities is 0. But when you get to -3, the sums of the probabilities becomes 1/6. So the sums of the probabilities goes from 0 to 1/6 when you just add the number x equals -3. That means the probability of x equaling to -3 has to be 1/6. It has to be the amount that you added to change the cumulative distribution function from 0 to 1/6. It was the jump, right? At x equals -3, you jump from cumulative probability 0 to cumulative probability 1/6, which means the act of adding one additional x value increased the cumulative probability by 1/6. That's probability is 1/6. Okay. The probability that x is equal to 4 is equal to, so when x is 4, it's in this interval, right? But we're not finding the probability x is at most 4. We're finding the probability x equals 4. If we wanted the probability x is less or equal to 4, it is 1/6, right? But the probability of x equals -3 is 1/6, right? And then when you take slightly larger values of little x, the cumulative probability stays the same. It stays 1/6. And so the act of adding the probabilities of these in between x values changes nothing to the sums of the probabilities, which means that the probabilities of any of these numbers in this interval other than -3 has to be 0, right? Because that's why it stays 1/6, because adding the probability of any of these x values in between doesn't change the sum. And so since x equals 4 is directly in the middle of it, not at the endpoint -3, the probability x equals 4 has to be equal to 0. It doesn't change. There's no new jump, right? there's a jump at x equals -3. The next jump is at x equals 6. And so before that jump at x equals 4, there's no probability added. And so the probability of x equaling to 4 is 0. Okay, so that's part A. And so, okay, so then very quickly, not going anywhere. I'm just going to do part B. It says find the probability, and then talk about the homework for a second. Find the probability function of capital X. So our little f of x here is then equal to this piecewise function. Okay, so it's equal to 1/6 for x equals to -3, which we already found. It's equal to 2/6 for x equals to 6. Why is that? Because when x equals 6, there's a jump from 1/6 to 1/2. And so when x equals 6, there's a jump from 1/6 to 1/2. How much do you jump by? You start at 1/6 and you jump up to 1/2. That's adding 2/6. That's adding 2/6. You start with 1/6 and you add 2/6, you get 3/6, which is 1/2. Which means the value, the probability at x equals 6 is 2/6. And then when x equals 10, there's another jump from 1/2 to 1, which means the probability is 1/2 for x equals 10. There's one more jump. It's at x equals 10. So the jump is at x equals -3 from 0 to 1/6. Another jump from x at x equals 6 from 1/6 to 1/2. And another jump at x equals 10 from 1/2 to 1. And it stays 1 forever onward. And there's no more jumps and there's no more x values with positive probability. And so that is the probability function of capital X. Okay, and so that's part B of that example. And that is the end of chapter 4. Okay, so for homework, I'm just going to assign the rest of the homework from chapter 4. Okay, so last time I gave homework, it was up to okay, so in homework 4, I want you to finish the homework from homework 4. So oh, okay, so you did 4.4 already. Okay, so oh, okay, good. Okay, so what I want you to do is homework 5. Okay, all of homework 5. Okay, so let me write that down. So the homework is homework 5. Okay, all of homework 5. It's not a long homework assignment. It's just I'm not breaking up into parts. Okay, so all of homework 5, and so that is going to be due. So today's Thursday, so you have the weekend. So this is going to be due October 2nd. Okay. Okay, so we'll stop here, and so I'll see you next class. Thank you. Okay, good. Okay, so.
Hey, Professor, I have a question, Professor.
Sure.
Professor, it's about the second test. Do you have any idea when it's gonna be?
So I haven't announced it yet. So
okay.
Don't worry about it. So I'll announce it with at least 2 weeks advance notice, and then you'll have that exam. Okay.
Okay. And Professor, one last about the final. Professor, final is gonna be in person, or is it gonna be same as online?
The whole course is online, so nothing's changing with regard to this class. Everything will be online for this class until the end.